Our immune system is built on a waiting game. It doesn't strike first. It waits for a virus to breach your cells or a pathogen to enter your bloodstream before it finally mobilizes a defense. And when it does fight back, the response can be deadlier than the invader. If you are bitten by a venomous snake or contract severe sepsis, it is frequently the body's own runaway inflammatory response that ultimately kills you. By relying strictly on the biological tools we evolved with, we are stuck acting as passive, vulnerable targets in an environment filled with microscopic threats. Nature, however, has already developed a workaround. The honey badger can take a direct strike from a highly venomous cobra and simply walk away without relying on traditional antibodies. This diagram illustrates exactly how, a genetic quirk known as the 18-7R mutation. It literally swaps the electrical charge of the badger's nerve receptors, turning them positive so they electromagnetically repel positively charged neurotoxins. While the badger achieves this through a molecular mutation, we can project a similar environment across the human body using electronics. By applying a continuous, low-voltage direct current to the skin, we can induce the same state of electrostatic repulsion at a macro scale. You can't just wire a person to a battery to achieve this. Human nerves rely on their own electrical action potentials to communicate. Flooding the body with an external DC field using standard wires would cause immediate crosstalk, leading to muscle spasms or cardiac arrhythmia. To maintain a permanent electrified state safely, we have to discard conventional metal hardware completely and build circuits using materials that speak the wet, flexible language of biology. The foundation of this system lies in epidermal electronics, essentially highly conductive, biocompatible electronic tattoos. We map the circuit onto the body using distinct, non-toxic inks. Graphene creates a primary surface mesh to distribute the charge evenly, while liquid metals like EGAN act as elastic hinges over your elbows and knees, ensuring the circuit doesn't snap when you move. This cross-section shows how the layout creates a biological Faraday cage. It restricts the direct current strictly to the outermost layers of the skin, insulating the critical, pulsing nerve endings deep below from any electrical interference. We now have a body safely wrapped in a flexible conductive mesh, but without a power source, it is merely a dormant engine waiting for fuel. Maintaining an active defense field requires constant energy. External batteries inevitably run out of juice, and tethering a person to a wall outlet defeats the purpose of the shield. We solve the supply issue by harvesting energy directly from the host. Piezoelectric nanogenerators embedded in the ink convert mechanical motion into electricity, turning every footstep and expanding breath into an active charge. Simultaneously, thermoelectric generators pull power from the temperature difference between your 98-degree skin and the surrounding air. Because heat transfer is intermittent, the circuit includes a supercapacitor ink layer. Unlike standard batteries, this flexible material absorbs and stores power instantly. This reservoir continuously feeds a stable 1.5 to 2.5 volts into the graphene mesh, ensuring the shield remains active even while you are deep asleep and completely still. The person wearing this ink is no longer relying on an external grid. They produce their own continuous power supply. With the field activated, we get our first layer of defense, electronic disinfection. Most bacterial cell walls carry a negative charge, so the continuous low-voltage field short-circuits the pathogen's membrane on contact, causing it to instantly leak minerals and die before it can colonize tissue. The second pillar relies on electrostatic repulsion. Taking a cue directly from the honey badger, the positive charge of the shield pushes away positively charged neurotoxins, creating a physical boundary against venoms. This visualization demonstrates the final pillar, electrotaxis. When skin breaks, the body generates a tiny electrical signal. The DC-charged ink amplifies this natural injury potential, acting like a GPS guiding stem cells straight toward the wound. Applying this exact microcurrent pulls regenerative cells to the site, speeding up soft tissue and broken bone recovery by 50. To see this working in sequence, let's look at a simulation. Subject X, equipped with the bioshield, wakes up and begins a morning run. As their feet hit the ground, the piezoelectric inks harvest the kinetic impacts. Combined with their rising body heat, the supercapacitor reservoir rapidly fills to maximum capacity. An hour later, an airborne virus settles onto their arm. Instead of finding a host cell to infect, the virus is instantly depolarized and destroyed. Later that afternoon, a sudden physical injury occurs. Rather than triggering a dangerous wave of inflammation, the DC microcurrent commands the immune cells to bypass the inflammatory trap and immediately enter a pro-repair state. By nightfall, Subject X is asleep and completely motionless. The stored energy in the supercapacitor takes over, continuously guiding repair cells to the injury site. The individual survives the 24-hour stress test intact because their outer barrier actively neutralized the threats long before they could breach the bloodstream. We spent millions of years relying on a biological immune system that waits to be attacked before it slowly mobilizes a defense. Epidermal electronics allow us to replace that waiting game with an instant, programmable perimeter. By interweaving our own body heat and mechanical movement with highly conductive inks, we bypass the physiological limits of our species. We take the energy we already produce and weaponize it, turning the human body into an active, self-charging fortress.